So hello everyone, I am Soumya and I will be demonstrating my blog which I wrote as a part of my course project in multimodal data processing. And actually I took a very simple topic, but I started with autoencoders, and I actually wrote a complete blog to how to use autoencoders and scale it to the cross-modal generative capabilities using variational autoencoders. And you can see actually a very nice way to break into the generative modeling. When I first started learning generative models, and parallelly I was learning probability, deep learning, and all other data mining courses in my as a part of my academic coursework, it was very tough to break into generative modeling at first. But when I saw autoencoders, actually we can use autoencoders to build many types of network. So this was my motivation, and also I wanted to write a blog, and thanks to multimodal data processing course project, so actually it gave me an opportunity to write a blog. So historically, I will be going fast in the beginning because I have a lot to cover in this blog. So historically, autoencoders were actually discovered by Geoffrey Hinton in around the 1990s, as far as I remember, and it was very similar to our biological neurons. And I will be starting with the simple autoencoder setup. In autoencoder, basically, if you know what is a multi-layer perceptron, in autoencoder, what we do is we feed in the input, we compress it to the latent space, and latent space is usually smaller than the input size, so it can be larger also. There are types of autoencoders, and at the output part it is a decoder and it is an encoder. So at the output, x is the same, like the output is the same as the input, because we are primarily using autoencoders for the, you can see in the figure, primarily using autoencoders for unsupervised learning, so we don't have an explicit label. So you can see this JavaScript visualization and play with it. And one thing usually people confuse with, actually I don't know how many people confuse with this kind of thing, but when I was working with the diffusion models, there is a unit architecture. Unit is an architecture. In unit, the output, the architecture can be symmetric, but here we feed in x and here we feed in y. The input and output should not match. It is not necessary to match in the unit. Also, unit is primarily used in the supervised setup, not in like in the autoencoders, which are mainly for the unsupervised learning. And unit is primarily associated with the computer vision tasks. Now, the mathematical formulation, it is very clear. See, for an input space x and encoded space g. So the thing is, encoder is what maps our input to the encoded space g, and decoder is something which actually maps our latent space to the actual reconstructed output, which should be same as our input. So mathematically, the loss function would be, here I am considering the L2 norm, so the xi minus the encoded and the decoded part. So the second part in the loss function is the reconstructed term, and the first one xi is the actual data, and we are taking the L2 norm. Surprisingly, we also know that we can do dimensionality reduction using PCA. So what is the point of using autoencoders then? Autoencoders, obviously it is a more flexible architecture, but in PCA also we can do PCA. We know it is linear. So what I did was, I don't know the theory, I actually discovered theory later on. I experimented in Kaggle. So the results were actually very much similar type of cluster on MNIST dataset, PCA and the autoencoder, after removing the linear layers, removing the activation layers, linear autoencoder. I actually attached the links of the IIT Madras deep learning course, and also the paper where they actually proved the part that linear autoencoders are equivalent to PCA. If we enforce some kind of orthogonality constraints on the weights of the autoencoders, we can exactly get the similar result. I didn't force the orthogonality on the weights of my autoencoder, but the results are still very similar. Just you have to rotate it. You can see the orange cluster. Just you have to drag that cluster to a point, and you can see the similar type of structure. So linear autoencoder, the loss is also the similar, just we drop the activation function in the hidden units and all the intermediate units. Now, a bonus thing which I would like to discuss is recirculation algorithm. Actually, you may skip this part, it is not relevant to multimodal data processing, but is backprop is the only way to train a neural network? No. Recirculation was also an algorithm. It was also discovered by Geoffrey Hinton in 1987. I attached the links, and it is not very popular nowadays in machine learning community because it was mainly for the unsupervised learning, and it is actually more mimics the human brain, this algorithm. So what I did was, see, suppose I take a simple example and I feed it in the values. So the thing is that do a forward pass and recirculate. Here actually one thing I would like to add is that we are enforcing W1 is W2 transpose and W2 is W1 transpose, because both are orthogonal to each other, like the normal autoencoder type of setup. So therefore the idea is we will first actually predict the output, and then we will recirculate the output to reconstruct the thing and take the difference. So I will go slowly here. So first we did the forward pass, which is very much clear, and the recirculation step is hrec equal to sigma W2 transpose into y. Now what is W2 transpose? W2 transpose is actually W1. So the thing is that H can be calculated by W1x. Now we are again calculating it via W2 transpose y. So what is the reconstructed H hidden layer? And after that, with the difference from the actual weight, we are updating the W1 parameter. So this is actually more similar to the human brain, because I can see what is this part. This is the output response of a neuron, you can consider, and this was the input. And we are updating it using the local input and the local output, not in the back propagation where there is a loss function and it actually updates the gradient in the entire network. So this is the example. You can see I have attached the example in my blog itself, the detailed calculation, like how the weights are converging. And note that it is for the recirculation. I actually did it for the unsupervised setup. Autoencoder where the input and the output are like the one we were discussing till now. Second is the sparse autoencoder. In sparse autoencoder, we add a regularization in the hidden layer. Like we don't want to fire all the neurons in the H space. We add a penalty for that. We add a penalty in the loss function. Denoising autoencoders. This autoencoder is what? Like in autoencoder is a deterministic mapping. If it is not variational or stochastic, it is a deterministic mapping. So it actually learns to point the data in exact to the same point. Like for every point in the input space, we have a deterministic mapping. So the idea of the denoising autoencoder is we actually transform the input into a with some noise and then train. So it will make our model robust. It will capture the variations. Now the thing which we are going to discuss, and the convolutional autoencoder is just we have to use the convolutional layers instead of the normal fully connected layers. And in variational autoencoders, which we are going to discuss now, is the main thing. In this type of autoencoder, it is stochastic in nature. We predict mu, sigma, and then we sample it. And then we sample from mu and sigma. We assume that it should follow a normal distribution. And then we feed it to the decoder. So now you may ask that how will the gradient flow? How can we connect Z? So we cannot connect Z directly. But the trick which we use is, it is known as the reparameterization trick. What we do is, we do not sample from normal mu sigma, we sample from normal 0, 1. Because normal 0, 1 is fixed, we can sample. And we can actually modify the sampling from normal mu sigma is mu plus sigma times the sampled data from normal 0, 1. And then we connect Z via this. Now we can actually take the gradient, del Z by del mu or anything, del Z by del sigma. Because E is like we don't want to train E. E is not a parameter. Parameter is mu and sigma. And what about the loss function? The loss function is actually the loss function of the variational autoencoder. We impose that the learned distribution should not diverge very much from our prior. PZ is usually normal 0, 1. And we want it to be close to the learned distribution Q theta Z given X should be close to PZ. So we impose a KL divergence term. Now, and the second term is normal. The second term is like the log P theta X given Z. Like we are maximizing the likelihood of the data points. Actually, we can reduce it to the formula if we assume normal distribution. It can be simplified, the DKL term. So I recommend reading Deep Learning chapter 14 and chapter 20 by Ian Goodfellow book in Deep Learning. Now applications you can read about. Now you must see, you can see the visualization. We are making mu and sigma, and then we are sampling Z and then reconstructing. So by now you have got a hint that it is a generative model. After training, what we can do is, we have mu, we have sigma, sample a value, and use the decoder to reconstruct it. So in this way, it can serve as a generative model. And one important thing which is very prominent in the variational autoencoder is that In variational autoencoder, there is a convex interpolation between the points. Like suppose you have a data point x2, and it maps to z1 and z2. What we can do is take z1, take z2, pick a point in middle of that line. It is not a line, it is a line in a high dimensional space, because the latent space is not necessarily 2D. Pick this point, call this z bar, and reconstruct it. You will get output, definitely. And this output will exactly lie between the reconstructed outputs. This is known as the convex interpolation, because the local space is almost convex in nature. And so food for thought. Like suppose we have a voice. For image you can see the result. I started with 2 and 7. These results are actually from my own notebook. I have provided the link. So I reconstructed 2, reconstructed 7, and I reconstructed a point in the middle. See how in the space it transitions from 2 to 7. The middle points, you can see the journey of the data. So it is actually very good. I highly recommend you reading food for thought part, the voice interpolation part. What I was thinking is that it is just my idea. I don't have enough data to train on. Like suppose you have two singers, Arijit Singh and Atif Aslam. Map their voices to Z1 and Z2. Suppose this is Arijit and this is Atif. Now take a point in between and reconstruct it and see how the voice retransforms, like the voice how it translates from Arijit's point to the Atif Aslam's point. You can do it using your own audio with your favorite singer's audio and see what are the differences. You can actually work on that part and modulate your voice. The possibilities are just endless. You can actually extend this thing to many modalities. Now at last, to multimodal generation. So in multimodal generation, I picked up a paper and implemented it completely on the MNIST dataset. MNIST dataset is a labeled dataset. I will be describing it. So the idea is that there are digits and the labels. So what I did is, it has 60K samples. For 30K, I kept the paired ones. Rest 30K, what I did is, I actually broke it into two parts, like just the image and just the label. Label, I did one hot encoding to make it look like a text embedding, and the image was just the image embedding, like just the image itself. So the idea they are presenting is, why do you actually take, like see, these E1, E2, En are different autoencoders, variational autoencoders. They are predicting mu1, sigma 1, mu2, sigma 2, mu n, sigma n. And what they are doing is, they are calculating mu equivalent and sigma equivalent and calling it product of experts. This technique is actually not very new in this paper. Product of experts is a well-known technique in machine learning community. So what they are doing is that they are clubbing this mu1, mu2, mu n, sigma n. Now how to club? Like are you taking a mean or doing some kind of clustering? No, the thing which they are proposing it. Since we are dealing with the probabilities, so the thing which they are proposing is that, see, P of Z given x1 autoencoder till xn modality encoder is equal to P of Z into pi of P theta xi z. This step is only true if we assume the independence of the modalities. Because we cannot directly multiply the probabilities, it is a joint distribution, we have to multiply it. We can multiply only if they are independent. So the thing is that, now we are assuming that it is a normal. So the idea is that x minus mu1 by sigma whole square, like the normal distribution is like this only, as far as I remember, sigma 2. The idea is that just multiply it and get an equivalent representation, and sigma bar whole square. Now this equivalent mu bar and sigma bar, which after calculation you can get it, I solved it using a numerical example. So first you have to calculate t, 1 by variance. As you can see that I have calculated t, 1 by variance for each data. Sum them up and name it combined precision. And the combined mean can be the combined mean is actually the weighted average with the precision term. And combined variance is just the inverse of 1 by tt is the total combined precision. And you can get the equivalent distribution. Now, what is the benefit of this architecture? This architecture is actually very scalable. They have used the term scalable because suppose I have an image encoder and a text encoder. We are doing it, we're generating the modalities. Like it is mu1, mu2, sigma 2, sigma 2. Now we are clubbing it. So the possibilities are just endless. Train them where I is present, text is present, and club it and reconstruct it. You can even train them when text is absent. You can even train it when, like for n modalities, like there are 2 raised to the power n combinations, 2 raised to the power n combinations of modalities. suppose if some modality is absent, just its contribution in the term will vanish, because in the real life we don't have data for exactly all the modalities present. So the thing is that it is very robust architecture. Like we have different modalities and we can actually train it on a data set where we have the data. We don't have the data for every modality for every data point. Now we train it and keep the architecture, and we can still get a mu and sigma final. And with this mu and sigma, we can regenerate any part. We can take the decoder and regenerate any part. Like we can do image to text, text to image, text to text. Just the possibilities are just endless. Like the generative capability of the autoencoder, we can keep it and keep on generating. So this is the thing which they proposed in the paper, and you can see it. And I attached all the references, books and videos for visualization. And for the JavaScript interactivity, I used Cloud 3.7 Sonnet, which is a LLM model, and GitHub Copilot for the image placement layout. And the tool which I'm using for writing is Microsoft OneNote. And I deployed my blog on Vercel. So the thing is that you can check my notebook also. It contains the full code implementation of all the parts and the result. Like, let's see if it loads. I'm just going at last. See, I told my model to draw 2 and it is drawing 2. I trained my model on MNIST dataset. One thing you can do is that for the text I used one-hot encoding, you can use BERT embedding. So it will be better. Like you can actually type in, like draw the number 8. It will still map it in the embedding space to the actual what are you meaning. So thank you. That was all from my side, and I highly recommend you reading my blog.